Properties of solutions. And if you'll harken back to chapter 4, which dealt with reactions in aqueous solutions, that was a specific type of solution, one in which we saw water quite prominent in the form of the solvent. But in this instance, we're going to develop a more broad approach to speaking of solutions. Now, by definition, a solution is a homogeneous mixture made up of two or more pure substances. Now, by homogeneous, we mean of one phase. So it's a substance in which we see two or more substances combined in one phase. Now, in a solution, we see that there are two parts. There's the solute and the solvent. The solute is the substance that is dissolved, while the solvent is the substance that does the dissolving. If we're talking about mixing salt and water to make a saline solution, then we would dissolve sodium chloride, the solute, in water, which would be the solvent. Also, just as a general rule of thumb, the solute is usually present in lesser amounts, while the solvent is usually present in greater amounts. And we can talk about different types of solute-solvent mixtures. Solid mixtures, solid liquid mixtures, liquid, gas. But in each case, the solute is dispersed uniformly throughout the solvent, and the solvent is what dictates the state of matter that the solution is in. Now, the ability of substances to form solutions depends on a few factors. Number one, the natural tendency for these substances to mix, as well as intermolecular forces that may be at play. The process of making a solution is called solvation, when the solvent in question is water. The term hydration is oftentimes used. So let's take into consideration the dissolving of salt in water. Salt, as an ionic compound, exists as a series of positively charged cations and negatively charged anions collected together in a solid crystalline lattice. When placed in water, the water molecules can interact with the positively charged cations and the negatively charged anions because of the nature of water. Harkening back to chapter 11, when we spoke of intermolecular forces, the extreme dipole that is set up, that we typically refer to as hydrogen bonding, allows for water to be both partially positive and partially negative. The oxygen, which has electron density drawn towards it, is partially negative, while the hydrogen, which has electron density drawn away from it, is partially positive. So in a solution, we see the solvent-solute interactions that will allow for the disruption of the sodium chloride solid. The partially positive hydrogens are attracted to the negative chloride ions, while the partially negative oxygen is attracted to the positive sodium cations. And if those interactions are great enough, then we will see solvation take place. Now, we don't want to necessarily confuse the formation of a solution with an actual chemical reaction. Just because a substance goes away when it comes in contact with a solvent does not mean that the substance dissolved. In some instances, we may see a chemical reaction that has taken place. Now, the process of dissolving or solvation is countered with the opposite process known as crystallization. So you can imagine adding salt or sugar to water. And if you stir, 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 then the solute will dissolve. But there will be a point beyond which you cannot dissolve any additional solute. This is known as the saturation point. Beyond this point, adding solute will not form a more concentrated solution. You will simply be adding solute that will not dissolve. And any solute that is dissolved that comes out of solution or reverses the process undergoes what we call crystallization. When the rate of these two opposing processes is equal, then we refer to the solution as being in equilibrium. A solution that is in equilibrium with respect to the solvation and the crystallization processes is known as a saturated solution. It has as much solute as the solution can handle. Up to that point, the solution would be considered an unsaturated solution. We have not added so much solute to get to the saturation point. Now, the saturation point that I just spoke of is also known as the solubility. The solubility of a solute is the maximum amount of that solute that can dissolve in a given amount of solvent under a given set of conditions, specifically a given temperature. A solution that has that amount of solute in it is known as a saturated solution. A solution that has less than the solubility would suggest is an unsaturated solution. Now, surprisingly, there is another type of solution. But before we jump into that, I don't want us to get confused. There's a solution that doesn't have the maximum amount of solute dissolved. There is a solution that has the maximum amount of solute dissolved. So what other type of solution could there be? Well, you may find yourself saying, well, there must be a type of solution that has more than the maximum amount of solute dissolved. Well, how does that work? If the maximum amount is the most that can be dissolved, then how is it that there's an additional type of solution? Well, there is something known as a supersaturated solution. Now, it should be noted that supersaturated solutions are not that common, and they have to be prepared typically in a very specific way. A supersaturated solution involves a solvent that holds more solute than is normally possible at that temperature. In order to create a supersaturated solution, we have to understand something about the nature of solubility as it pertains to temperature. As the temperature of a solvent increases, typically we can dissolve more solute in that solvent. So how a supersaturated solution is made essentially goes like this. We take a solvent and we heat it up beyond the normal temperature in question. We then add enough solute to that solution, which would be an increased amount of solute with reference to the lesser temperature. If we carefully cool the solution down, if we allow for the solution to carefully return to a cooler temperature without any type of disturbance, then the solution can maintain that amount of solute. Now, it should be noted that these solutions are very unstable. Crystallization can usually be facilitated by disturbing the solution, either by scratching the side of the beaker or flask, or adding a seed crystal, adding a sprinkling of the solute in question will allow for a rapid crystallization around that seed crystal. Now, there are a few factors that affect solubility. There are solute-solvent interactions. For gaseous solutes, when we're trying to dissolve gases in solution, then the pressure of the gas, as well as the temperature. We just spoke of how increasing the temperature of a solvent can typically allow for more solute to be dissolved. The nature of solute-solvent interactions and their role in solubility typically falls along the lines of the phrase like dissolves like. Ionic compounds will dissolve ionic compounds. Molecular compounds will dissolve molecular compounds. Polar compounds will dissolve polar compounds. Nonpolar compounds will dissolve nonpolar compounds. Now, that's not an end-all be-all. It doesn't necessarily explain all types of solutions. But in general, we do say that the stronger the solute-solvent interaction, then the greater the solubility of a solute in that particular solvent. At the table below, we see a series of gases. Gases where we don't see any dipole forces, we don't see any hydrogen bonding, we simply see those dispersion forces at play. And if you remember, the dispersion forces are susceptible to polarizability. So the greater the polarizability, the more likely we are to see forces, intermolecular forces, at play. So as we see going from nitrogen to oxygen to argon to krypton, we see an order of increasing size that we see an increase in solubility. You can dissolve more krypton than you can nitrogen in a given amount of water at 20 degrees Celsius and 1 atmosphere of pressure. When it comes to dissolving organic molecules or molecules that have a significant amount of carbon and hydrogen in them, we find that the greater the polarity of these molecules, the better the solubility in water. Water is a polar solvent. So polar molecules would be more likely to dissolve in water. Now, in general, the carbon-carbon backbone and the carbon-hydrogen bonds that we see in organic molecules are not very polar. So we don't see a great deal of solubility when those are the only bonds at play. But if we see OH bonds, hydrogen bonding can increase the solubility. Once again, we see OH bonds in water. So the polarity that we see in OH groups tends to enhance the solubility of these types of compounds in water. When it comes to liquid solubility, the instance in which we see a liquid solute and a liquid solvent, the term miscible refers to liquids that will mix in all proportions. A perfect case of miscibility involves the solution of acetic acid and water. If you go to the store and you buy a bottle of vinegar, that bottle of vinegar is likely going to be anywhere from 4 to 6% acetic acid by volume. In other words, most of what's in that bottle is water. A tiny fraction of it, 4%, 5%, upwards of 6%, is acetic acid. So acetic acid is going to be your solute, while water is your solvent. But we see that they mix in different proportions. Liquids that don't mix in one another are known as immiscible liquids. Let's take, for example, hexane. Hexane is a polar molecule, a non-polar molecule that is made up of carbon bonds and carbon-hydrogen bonds in the form of C6H14. Since hexane is very nonpolar and water is polar, these two do not mix. They are immiscible. From a biological point of view, the idea of solubility is quite important. There are certain vitamins that are non-polar. These are called fat-soluble vitamins, like vitamin A. They are readily stored in the fatty tissues in the body. But there are also water-soluble vitamins like vitamin C, also known as ascorbic acid, that must be included in your daily diet because they are not readily stored in the fatty tissue. Another factor which affects solubility is pressure. Now, while the solubility of solids and liquids are not appreciably affected by pressure, the solubility of gases is significantly affected by pressure. In general, an increase in pressure reflects an increase in solubility. So with a higher gas pressure, you can dissolve more gas in a given amount of solution. Temperature is also a factor that can affect solubility. For most solids, the general trend is that as the temperature of the solution increases, so does the solubility. So if you were trying to dissolve sodium chloride in water and you had too much sodium chloride, then increasing the temperature would allow you to dissolve more salt in the water. Now, the solubility is an actual measurement since it is the maximum amount of substance that can be dissolved in a given solvent. It is quantifiable. Typically, we see the solubility in terms of grams of solute per a specific amount of water. Here we see two images. One in which we see ionic compounds, ionic solids dissolved in water. And the other, we're looking at gases. So as far as the solids go, you will notice that all of the lines on the graph show an increase as we go from left to right. All of them except for one. Cerium sulfate, as we see. The solubility of cerium sulfate actually decreases as you increase in temperature. But note that that is the lone wolf of the bunch. Out of all of these, whether it be an exponential growth, whether it be a linear trend, we see that as we increase the temperature, we also increase the solubility. Now, since this is something that is indeed quantifiable, we can look and see that, for example, at 30 degrees Celsius, based on the graph, we see that the solubility of sodium chloride falls somewhere in between 30 and 40 grams per 100 grams of water. At that same temperature, we see the solubility of potassium nitrate between 40 and 50 grams per 100 grams of water. Now, for all gases, as the temperature increases, solubility decreases. So we see all of the gases in the bottom curve show a decrease in solubility at higher temperatures. Up to this point, we've discussed solubility and solutions in a qualitative manner, describing the qualities more so than focusing on the quantities. In our next lecture, we're going to speak of the specific amounts with respect to solutions, concentrations, how we refer to the amount of solute in a given amount of solution. Thank you for your time and have a great day.